Hello and welcome to my SpringBootChess app demonstration. Let's take a look at the source code. So here in the base package, we have application.java, and it's the default main method for a Spring application. That Spring Boot application detects that there is a controller, and that controller serves the backend board.json. In addition, we have a static folder that has an HTML page with a CSS script and some JavaScript, in addition to the images of all the pieces on the chessboard. Let's go ahead and start the app and take a look at the back end. So here we have Firefox open. Let's go ahead and hit the URL for our service and type in the address of the JSON. So here we've been served the board object. It tells us that it's white's turn. There's no kind of status of the board, such as in check. We have all these squares which have an XY location and may or may not have a piece with an owner, type, royal to indicate if it's a king, and if it's moved or not for the pawns. There was white's board, the middle, and black's board. In addition, we have a list of all legal moves with the starting XY and ending XY for all the possible moves. Let's take a look at the HTML page. This HTML page uses JavaScript to hit that service, bring back the state of the board, and then build it. I'll get my queen out first. The AI takes some time to think and moves. You can see when we click on a piece, it highlights all the possible moves that piece can make for everything. And if we refresh the page, we're given a new game. Here's the UML diagram that shows the board mover. The board mover has a single responsibility to apply a move to the board. It's given a board and a move, and it's expected to return a new board. Up here, we have the basic outline of the JSON object that we serve. A board consists of squares, which may have pieces, and moves. There are three classes that do the board moving. First, we just move all the pieces. Then, we check for check. Then, we promote any pawns if necessary. The move is fairly straightforward. Grab the piece at x1, y1, and move it to x2, y2. The more complicated part is generating the list of legal moves that are possible. In order to accomplish this, the board move generator is used. Given an active player, such as white or black, and a list of squares, it generates a list of moves. First, it builds a square status map. That is a map from square locations, which have X and Y, to square statuses, occupied by a friendly piece, enemy piece, or an empty square. Next, it uses the active piece extractor to get the list of all squares which have white or black pieces. For each of those pieces, the move calculator factory is consulted. It's given a piece named piece, and it provides a move calculator. The move calculator gets the possible moves for that single piece. I've broken down the types of moves that you can make into three categories. Pawns are a special case, but there are leapers, which can move once along a vector, such as kings and knights, and riders, which can move any number of times along vectors, queens, rooks, or bishops. Once the Move Calculator factory has built a move calculator for each of the pieces, all of that's combined together and the board move generator returns all the possible moves without regard to check. Next, the board mover check without pawn promotion uses a check detector to detect if a player is in check. It uses a royal piece extractor to get all the royal pieces. In standard chess, the only royal piece is a king, but this backend is powerful enough to do exotic pieces known as fairy chess. Once the royal pieces have been extracted, the board move generator will generate all possible moves that the enemy can make. If there is a move in which the enemy could capture our king, then we must be in check. The board mover with check without pawn promotion will prune any moves which will put us in check, or moves where we are in check and we make a move where we're still in check. Finally, the board mover with check pawn promotion will extract all the pawns, and if those pawns are at the back row, it will promote them to queens. Here we are back in the controller. We can see that the endpoint is board.json, and there are optional parameters for x1, y1, x2, y2 to allow the player to submit their move. First, we generate a move. It could be null if this is the first move and we're just setting up the board. If it's not null, that must mean we're making a move. We'll create a new board object by using our board mover and applying to the board the player's move. Then the AI makes a move. We call the AI package, tell it to decide a move based on the board. It comes up with a move. And should it come up with a non-null move, then we'll apply the move to the board to get the new board. And there is the case that no move was submitted, in which case we can assume this is the first page load, and we'll just generate the default board. Then we'll return the board back via the JSON, and the page will build the board. Here we have the UML diagram for the AI opponent. The AI implements two basic interfaces. The chess AI, which given a board, will decide a move, and the chessboard evaluation. Given a board, it will assign an integer value to it, such that greater integers indicate the AI is winning, and lower integers indicate the player is winning. The first implementation of the chess AI interface is a chess AI that picks a random move. It's fairly straightforward. It generates a random index of a move and submits that move. The first evaluation of the chessboard evaluation assigns a positive number to each black piece owned by the AI and a negative value to each white piece owned by the player. It then takes the value of all the black pieces minus the value of all the white pieces. For the initial board state, the value is 0. Should the AI lose a pawn, the value will be -10, and if the AI captures a player's pawn, the value will be +10. Next, for a more challenging opponent, the Minimax Chess AI class was made. It implements decide move, but has a private function pick the maximum moves. Given a board, it uses a board mover to figure out all the next possible moves. It assigns a value to each of these using the Minimax chessboard evaluation, then picks all the moves which tie for the high score, and will randomly select one of the high scoring moves. The Minimax chessboard evaluation relies on the initial evaluation and a recursive function, evaluateBoard. Given a board, it evaluates to a depth. At any time, should a board be the end of game, such as a checkmate or a stalemate, it will assign the appropriate value to that board. It sees all the next possible actions. Should it be black's turn, it will pick the maximum value because the AI wants to maximize utility. And should it be white's turn, it will assume that the player will minimize the value, doing what's best for their pieces. Currently, the depth is set to 3, meaning it will think about a move that it can make, the move that white can make in response, and the next move that black can make. Let's play a game against the random guessing AI. It's quick and responsive. We can even potentially put our pieces in danger without much consequence. Next, let's do the Minimax algorithm, but we'll set the depth to 0, meaning the chess AI will look at its next move and maximize utility. If we had to describe this AI in words, it would be, if it can capture a piece, it will. Let's start the service and take a look. Let's take a look at how this AI behaves. We might be able to set up a trap for this AI, because if it can take a piece, it will. Here, it moved its queen out to capture my pawn, but this is a bad move, because I can capture the queen. Let's increase the difficulty. By setting the depth to 1, it will no longer blindly capture pieces. It will check what it can capture, then it will check what I can do. It won't make the same kind of mistakes. Here we are at the increased difficulty. Let's set up a situation where it can take our pawn with its knight, but it will lose its knight. Let's see if it falls for it. Here, the knight didn't take our pawn because we could respond by taking the knight. Let's see if it's willing to trade its knight for our rook. It is, because the value of our rook is greater than a knight. It sees that I will be able to respond and kill its knight, but it's happy with the trade because it believes it's ahead. For our final demonstration, we'll set the depth at 2. This means the AI will think about what it can do, what white can do in response, and its next move. I'll start the service. Here we are at the next level of difficulty. You'll see that our move didn't happen right away because the AI has to think. This AI opponent is significantly stronger, and I'm unable to beat it, but I'm not very good at chess. Thank you for taking the time to look at my SpringBoot Chess application. You can find the source code on my GitHub, and you can find the UML diagram shown in the presentation in the resources folder. Thank you.